Hello, everyone. Welcome to my lab. I'm very happy to have you here. Are you ready to learn? Yeah. Are you ready to have fun? Yeah. Well, you know we must do the experiments in a very safe way. That's why I put my goggles to protect my eyes from potential damage. Before I did that experiment, I also want you to see that we have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, but it's a safety measure that we are taking. Now what I'm going to do at this end of the table, I'm going to take a large can. I'm going to take this cafeteria tray too and put it right here. Take a large can that has an opening. It's empty except for air. And I'm going to put a little bit of water in it, like so. And then I'm going to heat the water. I'm going to try to boil the water by putting the can on top of this tripod, below which is a burner. I'll turn the gas jet on and strike a match and light it. What I want to do is allow enough time to pass so that the water boils. When the water boils, we're going to see something coming out of the opening. It's going to be the condensed water vapor that we will see. So we'll get that going. I also want to get something else going at this end of the table. I have a beaker that has a volume of 2 liters. In it is a sheet of copper that has been cut in the shape of a tree. And I'm going to add to that a clear and colorless liquid to cover the tree. We'll come back and take a look at this reaction to see if anything is happening as we move on to do other experiments. What I want to do then, as we're waiting for something to happen, is to ask you to focus your attention at these 2 large flasks that I have. The bottom flask is filled with water. It has a volume of 5 liters. And the top flask looks empty. It's actually not empty. It has in it a colorless gas. It's invisible. The name of the gas we have in here is called ammonia. Now this flask that's filled with ammonia, which we cannot see, is connected to the bottom flask by a piece of glass tubing running through this 2-hole rubber stopper. And the other hole has in it this the bottom of a medicine dropper and this rubber bulb. The rubber bulb has some water in it. What I'm going to do is squeeze the bulb so I can squirt some water into the top flask and see if anything happens. That's why we do experiments. We mix things together to see if anything happens, and we try to be attentive about it. So here we go. I squeeze this. What you see happening here is the siphoning of the water from the bottom flask to the top flask. That happened because ammonia, the gas ammonia, dissolves in water. And the small amount of water I squeezed out of the rubber bulb here dissolved all the ammonia that was filling up the top flask and created a partial vacuum up there, causing the water to be siphoned from the bottom flask to the top flask. And we have an indicator in here to indicate to us that ammonia forms a basic solution when it dissolves in the water. So this is a kind of an interesting experiment that has to do with the effect of the solubility of a gas and then the fact that the atmospheric pressure pushes on the water and causes the siphon to go up. Okay, let's take a look at what's happening over here and see if we can see any condensed water vapor coming out. Can you see any condensed water vapor coming out? Let's make sure this is really going hot. You see some? There's some coming out, some evidence that this is going on. So what I want to do is use this cafeteria tray to put some ordinary ice in it. Just going to put some ordinary ice in here because I want to use this ordinary ice to cool the can. And to do that, I can't handle the cans with my bare hands because the can is very hot. So I'm put my gloves on again to protect my hands this time from heat, not from cold. And to do this experiment, I will take a rubber stopper and plug up the hole that's up there, all right? And what I will do is plug it up like so, lift it up, and put it on the ice, and we'll see what happens. The can got crushed. That's because the pressure inside the can got to be less than atmospheric pressure. And the question is, how did that happen? Well, you know what? You can do this very same experiment at home, but you don't need a big can like this. All you need is an empty soda can like this that you've emptied. You put a little bit of water in it, as I'll show you now. And you put it so that the water boils off. And what are we looking for? We're looking for evidence that the water has boiled. And what we're looking for is condensed water vapor coming out of there. So it takes a little while for that to happen. So we'll wait for that to happen. But we'll try to talk about why this happened. The pressure of the atmosphere caused the can to collapse, to be crushed. And this happened when after heating the water, and the water changed into vapor, the vapor was coming out of the hole, of the opening, and along with it, that vapor swept along with it some air. And when the air was swept out, and then I sealed it by putting the rubber stopper on, then I cooled it off in the ice, on the ice tray, then the water condensed, and the pressure inside the can got to be less than the pressure outside the can. So this is happening over here. So what's happening is that the pressure inside the can now is different, but I can't handle it with my hands because it's very, very hot. So I'll take these tongs, I'll pick up the can, and I'm going to flip it over and put it in this beaker. It has water in it, and we'll see what happens. So here we go. You see the can? Got crushed for the same reason we had before, and the can was not very clean. That's why the water is that color. All right. Sometimes in my lab, I get very, very big surprises, and I would like to ask you to welcome a very special friend of mine who has been helping out with these programs for many, many years. Is Elizabeth in the audience? Come on up, Elizabeth. Hi.
Hi.
How are you?
Fine. I brought you a special token because it's your 25th anniversary.
Oh, how sweet of you and how special of you. This is a very, very nice token. Do you know what metal it's made of?
Copper.
It is made of copper. You're right. And do you suppose we can try to change copper to silver? This is the silver anniversary of the show. Do you suppose we can try to do that?
Sure.
Would you like to try?
Yeah.
Okay. Well, what's the first thing we must do before trying?
Put on our goggles.
Well, I got mine on. So you put yours on. And we're going to do this experiment to try to change copper to silver by putting it in this casserole. That's empty. You see that? Put this in the casserole. Put it on top of the burner. And then add a clear and colorless liquid just to cover it up. And after that, what I'm going to do is add a solid, a metallic solid. And we'll have to just to cover it up. And then I'm going to take a match, strike the match. After I turn the gas on, strike the match, right? That's the proper way of doing it. And of course, we always strike the match away from us. So there, we'll let it heat for a while. You know, chemical reactions sometimes are very, very fast, and sometimes take a while to happen, and that's why we have to heat them up to make them go faster. So we'll wait for that for a while and see what else we might want to do here.
Okay. Well, I see you have another yellow balloon. Is there anything else you can do with it?
Oh, sure. I can do lots of things with balloons. This is a yellow balloon that has in it the gas helium. And what I'm going to do with this balloon is to add to it something that's left over from the ice cream experiment. What's left over from the ice cream experiment is some liquid nitrogen. So I'm going to put the balloon in this large dish, like so. I can't hold it. I can't let go of it because it'll go up, so I'll just hold it down like this. And then I'm going to add the liquid nitrogen to it, and we'll see what happens. You ready?
Yep.
Okay. Oh, I see some of you are covering your ears. Why are you doing that? Okay, I know why you're doing it, because you've had experience with balloons. So here's the liquid nitrogen, and you see what happens. The balloon, what's happening to the balloon, Elizabeth?
It's shrinking.
You bet it's shrinking. It's shrinking and collapsing because the pressure inside is lower than the pressure outside. We cooled down the helium, and the helium slowed down to the point where it exerts less pressure than it did before. And when the balloon warms up, then it goes all the way to the ceiling. Almost got a hit there, right?
Yep.
I'd like you to walk over to that bicycle wheel that we have at this end of the table. Do you see anything special about it?
There aren't any metal spokes. They've all been replaced with pieces of rubber tubing.
That's right. And what we want to do is learn something about the properties of rubber when rubber gets heated. Behind the wheel, we have a heat lamp. And if you throw the switch on, then you can turn the light on, and we'll see what happens.
Is this it?
Yeah.
Okay.
The light is on, right?
Yeah.
You see anything happening?
The wheel's starting to turn.
Are you pushing it?
No, I'm not touching it.
Nobody's touching it, right? So the wheel, this is a well-balanced wheel where the metal spokes have been replaced by pieces of rubber tubing. And as the rubber tubing is heated, then makes the wheel turn. So you and I are going to do an experiment to try to understand why that happens. And this experiment we will do with rubber bands. So here's one rubber band for you and one for me. And the way in which we will do this experiment is that we will use our forehead as a way of measuring heat flow in and out of a rubber band. Okay? So hold it up like this, right close to your forehead, and touch your forehead. What does it feel like?
It feels cool.
Okay, now take it forward a little bit, stretch it, and quickly put it on your forehead. What does that feel like?
It feels warm.
Right, so stretching the rubber band gives off heat, right? Now, take it forward, allow it to shrink, and touch your forehead. What does that feel like?
Cool.
It feels cool again, right? So stretching the rubber makes the rubber hot, right? And allowing the rubber to shrink makes it cold. So if we heat rubber, what's going to happen to it?
It's going to shrink.
And that is the explanation that helps us with the bicycle wheel that we have over there. Okay? You learned a few things about rubber you probably didn't know before.
Yeah.
Yeah, but you knew about this part, right?
Yeah.
Right? Yeah, right. Okay, great. Shall we take a look and see what's happening to our experiment over here? Okay, let's do that. And I need to fish it out. It's very, very hot. Let me turn the heat off. Ooh.
Ooh.
I'll have this beaker. Let me just clean it off and cool it down. And there we have a piece of what looks like it is silvery in color, but it really isn't silver. Because the experiment that I did here, I used the copper that you gave me, the copper token. I added some zinc chloride to it and some zinc. And zinc deposited on the copper and gave it this silvery look. So this is not real silver. Okay?
Okay.
All right, but thank you again for the token that you gave me here. It's very, very kind of you. You gave me this.
Does that thing over there have anything to do with your silver anniversary?
That flask, that's silvery? Well, yes, it does. Is there something that you'd like me to do to it or do with it? I'll just set it over here.
Can you pull off the rubber stopper?
You mean just open it up?
Yeah.
I can open it up very easily. Just take the rubber stopper off, as you suggested. looks like a genie, right?
Yeah. That's neat.
You like that, huh? I'll tell you what was in here. We had some hydrogen peroxide, very strong concentrated hydrogen peroxide, and we had a small tea bag that was held by a very fine thread. And when I took the rubber stopper off, the thread, the bag fell in because the thread wasn't being held again, and started this reaction.
Was there tea in the tea bag?
Oh, no, it was not a tea bag. It was just like a tea bag. What we had in there was some manganese dioxide. And the manganese dioxide catalyzes the decomposition of the hydrogen peroxide.
Okay.
Well, thank you, Elizabeth, very much. And
You're welcome.
I hope you enjoyed the rest of the show. Thank you very much. What we should do now is take a look at that beaker that I filled. The beaker that had the piece of copper in it before, that I filled with the clear and colorless liquid. And what we're beginning to see here is the outline of a silver-coated tree. That's because the liquid I used was silver nitrate, and the chemical reaction between the silver nitrate and the copper caused the deposition of silver on the copper. You see the solution is developing its own characteristic color. That's because the copper is going into solution. Well, this being the silver anniversary of the program caused me to go back and look to see if I had some notes and some objects from 25 years ago or so, and I did find some. Actually, I found these silver spoons, and they're tarnished. And what I'd like to show you is how we can remove the tarnish. We can remove the tarnish very easily if we use a commercial solution. Here's a tarnished spoon. All we have to do is dip it into the solution. And you see very quickly the tarnish was removed. The tarnish is a compound between silver and sulfur. It's called silver sulfide. And sulfides are in the air. They're in substances like eggs and so on. And they can be removed by using this commercial method of removal, the tarnish removal. I'll cool this off. I mean, I'll clean it off a little bit here so it's easy to handle. There's another way to do this, a very simple way. What you need is an aluminum pan. And if you don't have an aluminum pan, you just take any pan and line it up with some aluminum foil. And the next thing that you need is some baking soda. The third thing that you need is some hot boiling water, which I have right here. And I'll get it out. And I will take then some of the sodium carbonate that we have here, bicarbonate, and put it into the boiling water like so. And then take a spoon that needs to be cleaned out, a silver spoon that's tarnished, and add the hot water that has the baking soda in it. So that we cover it. And you see that we can remove the tarnish just as easily because of a chemical reaction taking place between the aluminum and the silver sulfide, and the silver sulfide. All right, let's take another look at the tree that we have inside the beaker and see how the white silver now is beginning to deposit. Isn't that pretty? Let me take this box here out of the way. There, you see. It is an interesting display for the chemical reaction between copper and silver. Now let's take a look at this large beaker, which has a volume of 4 liters. I want everybody to look at this beaker. Because if you look at this beaker, and I just told you its volume is 4 liters, you've learned how big 4 liters is. You can't unlearn it. You may forget it, but you can't unlearn it. This is how big 4 liters is. And I have 3.5 liters of water in there, and I have a stirrer. And I'm going to stir the water by turning the motor on. And then I'm going to add a clear and colorless liquid and a clear but slightly colored liquid into the vortex that's developing here. We'll see what happens, if anything happens. What does that look like? Looks like a tornado. You're right. That's why we call this experiment the tornado experiment. And what color is this tornado? Should we call this the orange tornado experiment? Okay, let's add more of this. Let's see what happens if we add more. And now it's more like a hurricane, right? And we add more of this. And what happens? More is better? Not always, right? But now it disappears. Add a little bit of this. I thought you said it's orange. Well, it starts out being yellow and then turns into, or now it turns into yellow. It was orange, or is it orange or yellow now? See, that's why we do experiments and we make observations about the experiments and try to learn about the behavior of different substances that we have. Okay, what I want to do now is use the same stirrer to do another experiment with another beaker whose volume is? 4 liters. Right, 4 liters. You've got that right. It has a stirrer in it. It's empty except for air and the stirrer. And I'm going to mix into this beaker 3 different liquids. Here's the first one. And here's the second one. Anything exciting happened so far? Not really, right? So the volume changed. Well, here's the third one. This is an example of what we call a chemical oscillating reaction. It has in it 8 or 9 different chemicals, including, you're not paying attention to what I'm saying to you. I know how exciting it is to see chemicals in action. Yes, this is called the Briggs-Rauscher reaction. It's named after 2 high school teachers who discovered it in 1973. And it has in it 8 or 9 different chemicals, including water, potassium iodate, sulfuric acid, manganese sulfate, potato starch, hydrogen peroxide, and a few others. And the yellow color that you see, not right now, but when they oscillate, that yellow color that you see right there is the color of what we call iodine, or in the vernacular, iodine. And then it combines with the potato starch to form this deep blue color that's almost black. And these oscillations continue for a period of time. And this is what makes science fascinating and interesting and also challenging in terms of trying to understand what it is that is going on in a reaction of that type. What I'd like to do now is a reaction in this special apparatus that consists of a glass spiral connected to a large glass funnel, and down at the bottom is a large glass flask. And I'm going to use a clear and colorless liquid and mix it with a clear and colored liquid. But I'm going to do this mixing in the dark. So here we go with the lights off. I'm going to mix those. There we go. This is an example, with the lights up, please. This is an example of what we call a chemiluminescent reaction. Chemiluminescence is the phenomenon whereby energy is released in the form of light, but not in the form of heat. I want to thank you all and urge you to do science and other things that are worthwhile in life, but don't forget, no matter what you do, science is fun. Thank you very much. Thank you very much. Thank you.